Hi everyone. In section 2.2, we'll look at graphs of polynomials of degree 3, 4, and so forth. We'll discuss ideas of infinity and limits in our examples. Let's go straight to bowls and snakes. In the long run, non-constant polynomial graphs will look like bowls or snakes. So let's get straight to Desmos. Let's look at y equals ax squared. These are parabolas. If a is positive, they open up. If a is negative, they open down. Let's now look at y equals bx to the fourth. Again, these are bowls. They're not technically parabolas, but they're bowls. If the coefficient is positive, they open up. If the coefficient is negative, they open down. Notice that compared to the parabolas, these ax squared guys, notice that these green graphs, y equals bx to the fourth, they're steeper far away from x equals 0, but close to x equals 0, if you zoom in, actually the green graph is flatter than the red graph. So notice that the higher the degree is, the flatter the graph is close to the origin. Far away from the origin, the green graph's actually steeper. And so forth. Y equals cx to the sixth. Again, bowls opening up or down. Flat, very flat, near the origin. For example, 1/2 to the sixth is very close to 0. So the graphs for y equals ax to the second, fourth, sixth, and so forth, where the exponents here are even and positive, the graphs of these are bowls. If a is positive, they open up. If a is negative, they open down. So for example, on the left, we have the graph of y equals x squared, f of x equals x squared. It's a bowl opening up. On the right, we have the graph of y equals the opposite of x squared. G of x equals the opposite of x squared. That's a bowl opening down. Now, in the homework, you're expected to be able to evaluate these kinds of long-run limits. Long-run limits. The limit of f of x as x approaches either infinity or negative infinity. Basically, when you're asked to evaluate a long-run limit, evaluating a long-run limit, then you're basically being asked the question, what are the y coordinates approaching on the graph as x approaches either infinity or negative infinity? That is, as we look towards the right forever and ever, in the case where x is approaching infinity, or in the case where we look left forever and ever, as x approaches negative infinity. We're asking, what is the y coordinate approaching in the long run as we look off to the right and as we look off to the left? These are what I call long run limits. And for these bowls and snakes, the answers to these limit questions will be either infinity or negative infinity, if you're dealing with these kinds of polynomial bowls or snakes. Okay. So in the case of y equals x squared, f of x equals x squared, as x approaches infinity, well, as x goes off to a million, a billion, a trillion, what's happening to the y coordinates? The y coordinates are also approaching infinity. So the limit of f of x as x approaches infinity will be infinity. As we look off to the right, as x approaches infinity, the y coordinates also approach infinity. They increase without bound. Likewise, what's happening as x approaches negative infinity? What happens as x goes off to negative a million, negative a billion, and so forth? Well, as x approaches negative infinity, still the y coordinates approach infinity. This is because of symmetry. So in both cases, the long run limits will be infinity. Now, the phrase go back to where you came from is often taken as rude, but here it's very appropriate. If you look at things left to right, what's happening with this bowl? This bowl is coming down from infinity, is coming down from the heavens. And then over here to the right, it's going off towards infinity. It's returning to the heavens. So it's going back to where it came from as you look from left to right. And bowls have that property. Look at the graph of y equals the opposite of x squared, this g function. This time, as x approaches infinity, as we look off towards the right, the y coordinates are decreasing without bound. The function values are decreasing, negative a million, negative a billion, and so forth, towards negative infinity. As x approaches infinity, the y coordinates, the g of x values, approach negative infinity. Likewise, as x approaches negative infinity, as we look off towards the left forever and ever, the y coordinates, the function values, are also approaching negative infinity. So again, these two match up. Bowls have that property where the two long-run limits will be the same. They'll either be both positive infinity or both negative infinity. Again, if you look from left to right, we're going back to where we came from. We're coming up from down below, like hell, I guess. And then as we look left to right, we're returning to hell. We're going back to hell. We're coming up from hell and we're going down to hell. All right. And both have that property. Now, what about the graphs of y equals ax cubed and so forth? Let's take a look here. So y equals ax cubed. Okay, so that's going to be a snake here, right? If a is positive, we get a rising snake. If a is 0, that doesn't count. That's a flat line, y equals 0. If a is negative, we get a falling snake. Likewise, y equals ax to the fifth. Sorry, bx to the fifth. If b is positive, it's a rising snake. If b is negative, it's a falling snake. Again, similar to the situation with fourth degree versus second degree before the bowls, the higher the degree, notice we're steeper far away from the origin, or x equals 0, out here and out here, but we're very flat. The green graph is flatter than the red graph as we get close to the origin. Similarly for y equals cx to the seventh. Rising snakes and falling snakes, steep far away from the origin, but very flat close to the origin. So here we have our snakes. On the left, we have the graph of y equals x cubed, the f function. On the right, we have the graph of y equals the opposite of x cubed, the g function. Now, answer the same questions that we asked before. What are the long-run limits? I'll do this. So what is the limit of f of x as x approaches infinity? And as x approaches negative infinity? What's the limit of g of x as x approaches infinity and as x approaches negative infinity? What will be your answers here? Remember, the answer to these, when you're evaluating these long-run limits, you're answering the question, what are the y coordinates approaching? And the answer to each of these will be either infinity or negative infinity. All right. So notice that with these snakes, you're running away from where you came from. So notice as you look from left to right, okay, you're coming up from hell, but then you're going up to heaven. Likewise, over here from left to right, you're coming down from heaven, and then you keep going down to hell. All right. So in the case of y equals x cubed, as x approaches infinity, the y coordinates also approach infinity. So as x goes to a million, a billion, a trillion, the y coordinates are going a million cubed, a billion cubed, a trillion cubed, and those are also approaching infinity. So that long run limit will be infinity. As x approaches infinity, this long run limit will be infinity. As you look to the left, negative a million, negative a billion, then you're talking about negative a million all cubed, negative a billion all cubed. Again, you're approaching negative infinity. So as x approaches negative infinity, the y coordinates also approach negative infinity. Notice that these are different answers. So to these long run limit questions, you're getting different answers. One's infinity, one's negative infinity. In the g case, it's switched. As x approaches positive infinity, g approaches negative infinity. And as x approaches negative infinity, g approaches positive infinity. But again, for these bowl and snake graphs for polynomial functions, in the long run, you're either going to get infinity or negative infinity for these two directions. Here you have a mix for these snakes. One's infinity, one is infinity, the other is negative infinity for these snake cases because you're running away. Okay, next, we're going to talk about why, when we look at polynomial graphs, non-constant polynomial graphs, in the long run, we're basically dealing with a bull or a snake.